We're going to take a look at Unit 1, Worksheet 4. And the idea here is to be able to accurately sketch out a velocity versus time graph to represent motion. But we have found as time goes on that sketching out a position versus time graph is sometimes helpful in that process. Number 1 says the object moving away from a position of 0 at a constant steady speed. So the most common answer people would do is they'd start at 0 and have a positive constant slope over here, which suggests it's a positive constant velocity. Remember that the slope of the line represents the average velocity for the time interval. So positive constant slope, positive constant velocity. Now there's another way that we could do this, and I'll come back around to these at the end and discuss alternative ways that we could answer these same questions. Number 2 suggests the object is standing still. If the object's standing still, as time goes on, the position's not changing. So if we said the object started at this position, as time goes on, it would remain at the same position. Now, with that said, it would be equally correct to say that the position versus time graph looked like this the entire time, or was on the time axis, or even below the time axis. So the idea is that it has to be a horizontal line. Because we know that the slope of the line represents the velocity, a slope of a horizontal line is not positive or negative, it's 0. So when we sketch out the velocity versus time graph, that horizontal line will have to be exactly on the time axis. Next up, number 3 says object moves towards a position of 0 at a steady speed for 10 seconds, then stands still for 10 seconds. Well, the most common answer would be to go constant negative slope for a constant negative velocity and then remain at rest for an additional 10 seconds. If we did that, taking a look at the phase change being from here to here, so for phase 1, we've got a constant negative slope, so that would be a constant negative velocity. For phase 2, the slope is 0, which means the velocity would have to be 0. Again, those dotted lines just representing what clock reading does the phase change from phase 1 to phase 2. Down here for number 4, it says the object moves away from a position of 0 at a steady speed for 10 seconds, then reverses and moves back towards a position of 0 at the same speed. So we set this up away from 0 at a constant velocity, and then moves back at the same speed, but in a negative direction. I didn't do a very good job on here. The angle of these two lines should be similar, just mirror images of each other. Phase 1, we've got a positive constant slope, which would be a positive constant velocity. Phase 2 should be an equally steep line, but it's a negative slope. So when we draw phase 2 of this, it should be the same distance from the time axis as phase 1. So again, the distance from here to here should be the same distance as it is from here to here. Moving on to side 2. Side 2 quantifies these velocities. At number 5, we have a starting position of 0 and a positive constant velocity. And we are encouraged to calculate slopes of these. If we start with the starting position and the final position, obviously our starting position is at 0 seconds, we're at 0 meters. And our final position is 4 seconds, we're at 4 meters. So we can do some quick math over here and say that the slope is the change of position divided by the change in time, which is 4 meters divided by 4 seconds, which equals 1 meter per second. Notice I've got a general equation, original values plugged in, and an answer. So with that said, from 0 to 4 seconds, we were traveling at 1 meter per second. It's important that we stop that at 4 seconds because we don't know what's happening from 4 to 5 seconds. Taking a look at problem number 5, we've got to break things into, problem number 6, we've got to break it into 2 phases. Phase 1 is from 0 to 2 seconds. So our change in position from 0 to 2 seconds, if you just take a look at those 2 slope points, we've traveled 2 meters in 1 second, which is 2 meters per second. And then in phase 2, which goes from 1 second to 5 seconds, we've gone from 2 meters to 4 meters. So for phase 2, we've got color code these so we can see where our work is over here. Change of position divided by change in time. went from 2 to 4 meters, which is 2 meters, and that took from 1 second to 5 seconds, which is 4 seconds. And that equals 1/2 or 1/2 or 0.5 meters per second. So how does that look on our velocity versus time graph? Well, for phase 1, that's the part we did in green. We said it was traveling at 2 meters per second for 1 second. And then for the second phase, we said we were traveling at 1/2 meter per second, which would be like here-ish, from the 1 second mark until the 5 second mark. And for our number 7 down here, looks like phase 1, we started at 2 meters and ended at 4 meters. So our change of position divided by change in time, we've got a positive 2 meters, which took 1 second, which is 2 meters per second. Our slope for phase 2 is a horizontal line, so the slope will be 0. And then for phase 3, it starts at 2 seconds and ends at 5 seconds. We're gonna have to be careful here, because the change of position divided by change of time. The change of position, it ended at 0 meters but started at 4 meters. So our change of position is negative 4 meters divided by, from 2 to 5 seconds is 3 seconds, which equals negative 1 1/3 meters per second. So checking out what this velocity versus time graph, phase 1 lasting from 0 to 1 second is 2 meters per second. Phase 2, the green part, we said was from 1 to 2 seconds, and our velocity is 0, so that'll be on the time axis. And our third phase from 2 seconds to 5 seconds would be negative 1 1/3 meters per second. So we did say that we could do some additional things with these. What I've talked about so far is all that would really be expected. But if you wanted to stretch yourself a little further, check out number 1. What's a different way that an object could move away from 0 at a steady speed? Well, couldn't it also do this? In which case, what would the velocity versus time graph? Constant negative slope means a constant negative velocity. The next one, the object is standing still. I did a variety of these. You could be on the time axis, and that would be appropriate, or start at some negative position and remain at rest. Either way, the final result would be the same, that we've got a constant velocity of 0 because you're at rest. What would number 3 and number 4 look like? How would that affect the corresponding velocity versus time graphs? Taking a look at the velocity versus time graphs on the backside, we could use these velocity versus time graphs to practice finding the area under a velocity versus time graph to represent the displacement. So you could calculate displacement of these by doing the area of the rectangle which is equal to the height times the base, and the height in this case is the starting velocity times the base, which is our change in time. And so for this specific problem, it was traveling at 1 meter per second for 4 seconds, which equals 4. A meter per second times the second. The seconds cancel out, leaving us with units of just meters. So the displacement would be 4 meters. How about when you've got more than one phase change? Check out number 6. During phase 1, we've got this green rectangle. So if we check this out, we go area of this rectangle is height times base. The height of the rectangle is the starting velocity. Our base is change in time. That starting velocity is 2 meters per second, but that only lasts for 1 second. So during that green phase, phase 0 to 1, our initial displacement from 0 to 1 second is 2 meters. But that red rectangle, we have to take care of that as well. Oh, I should have highlighted my green rectangle earlier. With this red rectangle, starting from 1 to 5 seconds, that displacement is going to be the area of that rectangle, which is height times base, which again is initial velocity. Well, actually, it would be velocity initial times our change in time So our initial velocity for this one is 0.5 meters per second, and that lasts from 1 to 4 seconds. So that change in time is 4 seconds long. Half of 4 is 2. A meter per second times seconds. The seconds will cancel out, leaving us with units of 2. And so that's an additional 2 meters. So we take the initial 2 meters from phase 1, an additional 2 meters, and you'd have to add those together to get a total of 4 meters. And if you look at the position versus time graph, our starting position is 0, our ending position is 4, so that reinforces that. How would we have to take a look at things differently for this last problem when you've got phase 1 is a positive displacement, but phase 3 is a negative displacement? What would those look like? I hope that helps.